curve or not to curve? That is the question. And if you do curve, how do you do so fairly? I've invented this Desmos simulation that will help you curve exams using one of 4 methods and compare them. See mrhosey.com/Desmos. It'll be simulation number 22. Let's start with, is it reasonable to curve? An online colleague of mine, Dan Burns, once said that you either curve the exam when you write it, when you grade it, or after the fact. And I think as long as you're asking difficult, challenging, worthwhile questions, that's true. It's not true in all situations, but certainly it's true in a lot of challenging physics questions and a lot of standardized tests. So if we just accept that and you want to come up with something fair, what's the best way to do that? I took 4 methods, giving a fraction of the points back. Another popular one is to take the square root of the grade and multiply by 10 because, well, square root of 100 is 10. Another one is to take the standard deviation and the mean and just shift the mean to whatever it is you want it to be and use the same standard deviation, or at least the same z-score or smaller, and basically keep the order of the people the same but change the distribution. You could basically invent a polynomial or really fit it to some data and use that. So we're going to try these 4 methods and see how they come out. I'm going to try unsuccessfully to keep this video short and not get too much into the minutia of using the Desmos. So here are 35 raw scores on the bottom and the relative frequency for 35 questions. The mean was about a 49 and the standard deviation was about an 18. Would this be fair to curve? Would you feel any differently if I drew in a bell curve corresponding to that data and the cutoffs for A, B, C, D, and the majority being an F? Hopefully I've sold you on the occasional need for curving, but what do we want to consider when we're doing it? Things I think most people like to look at are what the highest score, can it be over 100? What's the average going to be? What score should pass? Can someone get more than 100? And can somebody's scaled score ever be lower than their raw score, which would certainly rub people the wrong way if I was a student. What we're going to look at is 2 dimensions. One, what does a graph of the new score versus the old score look like, i.e. what's the curve? And 2, what's the graph of the new distribution look like now, i.e. how many people pass and how many get A, B, C, etc. The underlying thing we look at, I hope, is does it seem fair? When I do need to curve, one system I've used for a while now is to give a fraction of the points back. It's progressive. The more points you miss, the more you get in return. So if we leave the maximum score 100 being an actual 100 and somebody can't get over 100 and they won't be penalized, this would give back 40% of the points. So a person who got 0 points would actually get a 40, but a person who got 99 points would get a 99.4. Method number 2, what you see before you is what a lot of teachers use, where they take the square root of the score, it has to be out of 100, and then multiply by 10, and that has a similar effect in that the better you do, the less benefit you get, and it also has the advantage of always being greater than your raw score. So everybody gets helped somewhat, but the people who score worse tend to get helped more. Now, I added a couple other features, like you can shift it vertically up or down, like just tack on 10 points or something. And if you wanted to, you could even shift the score before you raise it to a power. Also, the power doesn't have to be a half, meaning square root. It could be any power you want, and the multiplier doesn't have to be 10. It could be any multiplier you want. The third method is one that's pretty common, where you take a distribution that's supposedly normal, and everybody has a z-score for their score, meaning how many standard deviations away from the mean was your score. So what you do is you say, I want the average to be, in this case, 80 instead of 50. So you start at 80, and then what you do is for the new standard deviation, so you make up a standard deviation, and let's say that standard deviation, the new one, was 10. If your score was 2 standard deviations away, you would change your score by 20. So if you were 2 standard deviations below the mean before, you're now going to have a score of 50 minus 20 would be 30. Not that my numbers match the screen, but just wanted to make a point. So it's not enough just to tack on points to everybody's score. by changing this, by changing the new standard deviation, you squish or widen this new distribution. This last method, method 4, is polynomial. So I'm pretty sure New York State does something similar for the Regents exams. I've done fit with their data, and I seem to get a polynomial. So what I did is I dragged 5 dots, you can't see it on the screen here, have Desmos try to fit it, and then say, all right, well, those are going to be my coefficients for x cubed, x squared, and x. If you're going to do this, you got to be a little bit careful that you don't wind up with somebody losing points, or that somebody with a lower score getting a higher score in the end. So is the fit good? So this orange line represents 1 to 1, meaning it's the raw score. If you got a 20, you get a 20. If you get a 60, you get a 60, etc. All of the methods I tried here, I have the parameters set so that it always helps you. You don't want to have somebody where it's going to hurt your score. That's not cool. The red is the polynomial, the blue is the square root, the purple is the giving a fraction of the points back, and the green is the enforcing a new average and standard deviation. What you can also see is the number of A's, B's, C's, and D's for each. And if you were to assume a normal distribution, so here's the part where I have to be careful not to talk a lot. First of all, let me turn off the 4 fit methods so it's not so cluttered, and the same with the grades. And what you're looking at is the raw scores. This is the conversion, which is 1 to 1 here, and then this is the relative distribution. If you're interested in entering your own data, what you can do here is just delete these and type in these, or you can add a new column, like let's say Y5. By the way, if you type the underscore key after the first letter, you can make it letters. So for example, Y new data or something like that, and enter yours. You can do so. And then you have to change this here to match that. This is what data is being fed into there. So you can have different sets of data and feed it in there. You can also paste data in from somewhere else like Excel, but I've noticed it has to be 2 columns. So you just go to a new spot there, and then you would Control V, paste it in, and it shows up there. And whatever this is, remember, go back here and make that the same name. So in this case, Y1. So you've already seen where to put in the raw data, and you've seen how to toggle the different methods on and off. Let me show you these toggle switches. So what this does is it turns on information and turns it off. So let's say we don't want to see the stuff down here about the distributions. What you can do is you can either turn it all off, meaning show probability, set that to 0, and that turns it all off. Or you can individually turn on and off the normal curves. So let's say you just want to see the actual data and how that translates. Or you can turn on and off the data points because you might find that cluttered, or you might like to look at it. You can also drag these up or down. They're just the relative frequency. Now let me show you these handles, these fit handles. If they're on for the method number 1, I can just drag these up or down and it changes the fit, and you can actually see how that's changing the distribution of the data all live, which is pretty neat. The other thing that's changing is in this table, it's comparing the methods. So method 1, 2, 3, and 4 and 5, 4 methods, and the number of A's, B's, C's, D's, etc. If you click the grades, it will show you the designation lines for A, B, C, or D. And if you look in grades, you can change the cutoffs for what's an A, B, C, D, etc. You can see a scaled table, which is going to show you what the scaled score is for every possible raw score, and the scaled results, what the data you put in, what that translates to with the 4 scales. For method 2, you can change the power, the multiplier, shift, and shift before the power. For method 3, you can change the average you're trying to set it to, and you can also change another point on the line, and the standard deviation will be changed to match what you have selected. So the polynomial has 5 black dots here, these handles, and Desmos is fitting the polynomial to those 5 data points. So just drag those around and be careful. MrHosey.com/Desmos, it'll be number 2, and hopefully you found this as interesting as I did.